Everybody. This is Giovanni Santostasi. I am the Scientific Bitcoin Institute Director, and I am here with Stephen Perinov. It is the Vice Director of the Institute. This is an official show from the Institute. We introduce it a few times. I can tell you more things about it in a moment. This is episode number 44, right? Yeah, 44. That is kind of crazy that we keep going in these explorations of Bitcoin. For people that maybe never saw the show before, we are bringing up different tools from physics, from science. It's all, we are not debating things like, oh, maybe if this happens, if the interest rate go up, and then, because these are all a bunch of words in my vision. We look at the data. We are trying to see what Bitcoin itself is telling us. And we are using these tools that we learn from our career in physics, but also in other fields where we apply similar tools. And we go deeper in trying to understand what Bitcoin is telling us, both in the short term, but also mainly in the long term. It's not just about the power law, but many different other way of thinking about Bitcoin scientifically. And by the way, yes, this is, like I say, this is a show that is sponsored by the Scientific Bitcoin Institute. This is a non-profit organization that has been created just last year, the end of the last year. We are relatively new. We have a website that you can go and check. It's a work in progress, so don't mind the mess. We are improving it over time. The website is Scientific Bitcoin Institute, all one big word, .org. And there be eventually, will be a point of reference for all our research. We will post our papers there, maybe some different type of research, even other people research, students, projects. There'll be classes there, live graphs that you can consult. It's going to be a point of reference in understanding Bitcoin in a scientific way. So please visit and look at it. And we are not ready to accept support yet. We have our own budget and our funding. Eventually, this will be a project that has to be supported by the public because that is its function. We want to interact with the public. We want to offer services both to corporation, but also the individuals, the community. But eventually, if you want to support us, there will be both donations that you can give to the institute to support all our projects. We give grants to different institutions, different universities around the world, and also membership programs that are going to have benefits with it, like maybe indicators and newsletters and all kind of different benefit that you can get, perks that you can get by becoming a member. In particular, if hopefully thinking that you are actually supporting scientific research in Bitcoin and making Bitcoin a valid subject for scientific investigation, it's good enough, as a benefit itself. I don't know if you want to add anything, Stephen.
Yeah, I would just add that actually this is a great area to think about citizen science, So our members may contribute ideas, they may contribute data, perspectives on data. And so there's a role for citizen science in exploration of Bitcoin as well.
Absolutely. Yeah, we are going, in fact, that could be a good idea if somebody has a project, something that they want to explore. We can support you, we can feature your work, of course, with some vetting. That is part of the function of the Institute, because there are a lot of people posting online. That is great, because everybody, it's a free country, everybody can express their opinion about stuff, etc. But I think there is a place for having a group of people. It's not gatekeeping, but some quality control about, this is makes sense. There's some valid methodology behind it. and this other doesn't. This is why we want to have like sometimes people show these charts. Oh, the power load is doing this or this other. Is you know we want to have our own official version of the power law just to make sure that the right math is followed, the right procedure are followed. But we are also open to contribution from the public in general, because it's a great idea, in particular nowadays with the use of AI, etc. A lot of people can explore ideas, go deeper in understanding data. Of course, it needs to be done with the right methodology and with right knowledge. But yeah, it's a great thing. We can do this together as we explore what Bitcoin is. Okay, we can start the show. And feel free. This is an interactive show. It's a live show. We are taking your questions. If we don't answer immediately, you can ask the question on X, on YouTube, on Twitch. If we don't answer immediately, it's because usually we reserve the answer to the end. We do our presentation first, then at the end we read your questions. Okay, so feel free to interact with us and ask questions. And also, please subscribe to the channel. We just linked this show to our Scientific Bitcoin Institute YouTube channel, so go to that channel too and subscribe, and support in any possible way, even just with a click, this work that we do. Thank you. All right, Stephen, are you ready with your presentation?
I'm ready to share that window. Okay. Today, April 22nd, is Earth Day. So there's a picture of the Earth, a very recent one from the Artemis 2 mission. It's also Robert Oppenheimer's birthday. And actually, my undergraduate thesis advisor was a student of Oppenheimer's and spent some time at Los Alamos. But today I want to talk about twist and writhe, which are aspects of topology. And that topology may live in just a regular geometric space, or it may live in some other sort of space. And with respect to Bitcoin, our space has a backbone defined by the power law, but there's also log periodicity. So that's the connection with twist. And then I'll define what writhe means as well. First, I want to show just a posting on Substack by Sylvain Sorel, who's a well-known writer on Bitcoin topics and some other topics in finance on Substack. And he took notice of the power law and wrote a whole article about it. And I think he captured the essence pretty well, at least based from the headline and the graphic that he put together. Then I'll talk about several examples with sandworms, the ones from Dune, DNA, and magnetic field lines that are examples that manifest twist and writhe for their topology. And then I will take that into the Bitcoin space, and in particular, analysis of the log periodicity nature that sits around the core backbone of the power law. And the analogies with twist and writhe is what is not explained by the log periodicity. So I'll show a Fourier transform of the residuals, and then I'll get into the log periodicity fits. And I will show you that mainly the fundamental mode dominates. And I'll also show you that twist is more important than writhe. The log periodicity endogenous structure of the residuals has more energy than what's left over, which is the writhe or exogenous component. And it's even more true in bubbles. Writhe is close to half, but it's a minority. It's important to use log spacing for data analysis, and I'll show you an example as to why that's true. And we'll also talk about whether things change with time. Does energy move between the fundamental and higher order modes, harmonics? And there's evidence for that. So I'll show you some of that. Okay, first, this is just an image from Sylvain Sorel's Substack. And the title that he used for the article that he posted was Decoding the Bitcoin Power Law, How Network Physics and Epidemic Mathematics Drive the Price of the World's First Cryptocurrency. So he captured the essence of the two power laws that we talk about. And this is basically a post that he made that's a review of the paper that we've put up on zenodo.org, that, the mathematics of Bitcoin that's arising from the Metcalfe scaling. So he's capturing that as the network physics, and then how the adoption grows with time, which is the epidemic idea, the viral adoption. And then he's got this image, and I think it kind of captures things. He's got Metcalfe's law as in 1.8 power. He's got the overall scaling, 5.7. He took all these numbers from our paper. And the paper has now been submitted to a journal, and it's in review for the journal. So we hope to have news about that within the next number of weeks. And so I thought this was good that we got this visibility because he's pretty well followed. Okay, and then now transitioning into the twist and the writhe, I just want to talk a little bit about emergent physics. And this is a quote from a Nobel Prize winner a long time ago, in 1977. But he won his prize for work on investigations of magnetic systems and disordered systems. He also worked in particle physics and in high temperature superconductivity. And he worked on fields where you showed emergent phenomena. And so here's some writings of his that new physics can emerge when systems get large enough that you break symmetries. And by construction, if you like, these emergent properties can be completely unexpected and intellectually independent of the underlying laws. Bitcoin's behavior is an example of that. There's symmetry, but there's also symmetry breaking. And in particular, the log periodicity is discrete scaling. It's discrete scale invariance, and it's breaking symmetry that's first established by the continuous scale invariance of the power law. So we have systems as diverse as DNA strands, magnetohydrodynamic flux tubes, and the sandworm of Arrakis that have topological structure with the interplay of twist and writhe, which are scientifically defined terms for typology. Bitcoin evolves as a filament whose geometry in this space, in the space defined by the power law, essentially, partitions into twist and writhe. And then bubbles are phases of strong coherent twists. That's what I want to try and show today. So the first analogy is the sandworm. And here, the twist is the rotation about the worm's axis. And it's got this segmented body that allows it to, crawl along the sand and in the sand and rise above. But it's rotation about the travel direction that's twist. And writhe is everything else. And in these topological descriptions, one defines a linking number, which ends up being kind of an invariant for a lot of situations where the linking number is the combination of the twist and the writhe. And actually, energy can flow between the twist and the writhe. So in the sandworm, you've got a centerline path. In Bitcoin, you've got the parallel backbone. CSI is continuous scale invariance. You've got the ring segmentation. For us, we have the log periodic oscillations, which are the discrete scale invariance. And for the sandworm, you've got torsion around that axis. So it's how the rings are moving around in a torsional way. And for us in Bitcoin, we have the log periodic phase, which is the twist. So it's described by a frequency, which is this small omega, the log of the time plus phi, which is the phase parameter. And that tells you how far around you are in your twist. And then you've got, with the sandworm, you've got large scale bending of the worm. It can go in various directions, up, down, down into the sand, left, right, etc. And so these, in Bitcoin terms, these other deviations we categorize as writhe, and they're mostly exogenous. So twist is endogenous to the structure of Bitcoin, and writhe is exogenous influences that could come from macro or regulation, news events, various sources. Now, some of the early work for this was done actually in DNA topology with this defining of this linking number as the twist plus the writhe. And for DNA, the twist is just the regular periodicity that you see in these double helix strands. And you end up finding that there are about 10 and a half base pairs with the linkage between the two strands per cycle. So a full revolution in 2 pi or rotation in 2 pi, or from one peak to the other, averages about 10 and a half base pairs. And then the writhe is other things that happen. The DNA can fold and move around, because it's sitting there in a 3D medium. And the linking number is the combination of the two, the twist and the writhe. Then we can look at magnetic fields, which we see in astrophysical plasmas and many other environments. They're important for fusion research, for example, for confinement. But here's a case with the illustration of a solar flare and the magnetic flux tubes that rise from deep inside the sun below the photosphere, but move out into the chromosphere and into the corona. And these flux tubes, the idea is that you've got twist around the central axis, and the sun is differentially rotating. There's a difference between the equator and higher latitudes, and this causes these field lines to twist around. And then eventually you get shearing and instabilities, and you get release of energy and flare events. And this can affect the Earth because particles get accelerated and hit our ionosphere. The writhe is the movement of the axis itself. So the twist is the rotation around. And so that's like the log periodicity with Bitcoin moving around the parallel core. The writhe is the movement of the axis itself. So that's deviations that are not of the twist kind. I actually came across a paper by Berger and Field, written in 1984. Well, Field was my PhD thesis advisor, and I just came across this paper 2 or 3 weeks ago. I was not aware of it. And he wrote a paper about how the linking number can be conserved even with some reconnection of the magnetic field lines. And the paper's turned out to be a classic. It's still used. And they actually drew on DNA to inform the way they constructed their model. So twist, coherent log periodic modes for Bitcoin wrapped around a parallel core. And the flare events and the reconnection of magnetic fields, where you get these kink instabilities and the lines break and reconnect with other field lines, we can have as an analogy between bubble release and crash in the Bitcoin world, as a rough analogy. And this shows the abstract of their paper. The concepts of twist number and writhing number are introduced from the mathematical biology literature. So they actually drew from the DNA model to describe the contributions to helicity from twist about the axis of a flux tube. So they're trying to show that helicity would be an invariant, that you would have the flux of helicity through space. So my proposal is that you think about Bitcoin log periodicity as taking the role of helicity or twist. Now, the first thing that one can do is do an FFT. And so you remove the power law and you get the residuals in log price, and you can do an FFT analysis and see where the frequencies are and see where the power is as a function of frequency. And it turns out that the peak corresponds quite nicely with what we've been using for our log periodic fundamental number. The spacing number, lambda, is just around 2. That corresponds to an angular frequency of close to 9. And for lambda equal 2.05, which was a best kind of a best fit here. You get 8.75. Well, this graph uses a different scale for frequency. On the x-axis, it uses cycles per log 10 decade, and the peak is located around 3.2. There's a formula that relates that. You have to multiply by 2 pi, and you have to divide by the log of 10, but then it converts directly. It's a direct linear relationship with this lowercase omega of 8.75. We've also marked the harmonic. So the red vertical line is the fundamental, and you can see most of the power is there, and the y-axis has power logarithmically. So there is a lot more power there than there is in other modes. There seems to be some power around the first harmonic. Well, they call it the second harmonic, but it's really the one that's 2 times the fundamental. And then there's 3 times the fundamental is the blue, and 4 times is the purple. And we can see that there's some matching up with the second, third, and fourth product of the fundamental. There's a really interesting dip between the third and the fourth. And also there's a peak is a little earlier. It's around 2.7 times the harmonic, which is interesting because when I did a fundamental plus a synthetic, that's what was found for the synthetic was 2.7. But if you add up the weighting in these 4 modes, and you have to put a little window around, and the window is plus or minus 1 in this frequency measure of cycles per log 10 decade. And actually one window was 0.8 and one window was 1.2, just to measure the sensitivity there. And in either case, you find that about 70 to 79% of the power is in those 4 modes, the integrated power within the windows, the 4 of them summed up. And the breakdown between the fundamental and the others is about 70% in the fundamental, 73% in one case, 0.65 in another case with the wider window. So it's quite fundamental dominated. And then what's left over is the writhe, and that's 21 to 30%. And that's what you can consider exogenous. So coming out of just the FFT analysis, you'd say around 70% or so is in our twist, and the rest is in the writhe. The dip, you can say, is evidence of a coupled system between harmonics. And it's one of the reasons why what's called the 4th harmonic here, which is 4 times the fundamental, sometimes has more energy than the 3rd. It's actually more symmetric. Okay, now I wanted to show you the difference between using linear spacing on your data set and logarithmic spacing. I used a weekly data set that extends from the middle of 2010 until early April of this year. There are 875 data points with linear spacing. And when you do that, you get an R-squared of 0.49. You get a standard deviation of 0.21 in log 10 space. And you find an omega of 8.8, which corresponds to a lambda log periodic spacing parameter of 2.04. But it only put 34% of the twist because you're overweighting more recent data. And what you really want to do when you're studying something that's a power law system is you want to do log spacing. The FFT that I just showed you has log time spacing. It interpolates onto a logarithmic grid. So if I redo this with log spacing, where I selectively pick out of those 875 weekly data points, 200 that are more or less logarithmically spaced, even though I have many fewer data points, I get a higher R-squared. I get 0.61. And the standard deviation is essentially just as good. It's 0.22. The omega is this 8.75 that I mentioned on the prior slide, and that corresponds to a lambda spacing parameter of 2.05. But importantly, it puts 61% of the energy into the twist. So this is the importance of using log spacing analysis on your data set. Okay, this one is showing from the linear space as just a first look with only 2 modes. And this mode is a fundamental, in this case 8.84, and 1 overtone, 1 harmonic, the first harmonic, which is twice the frequency. And in that case, what you see is a fit in the upper right-hand graph of that triptych. You see it fits kind of okay. It fits well for the 2011, 2013 bubbles, reasonable for 2017. It does not fit 2021. You don't expect it to, because that was not a fundamental bubble. You do see some power in the 2021 bubble, which is the last of the 4 in the overtone. And then the red line is the total of those 2. If you look in the chart on the left-hand side, you see that over time, the energy fraction in the fundamental is falling, and in the Writhe term, the remainder, it's rising. So in this case, it was saying that overall the Writhe was 0.66 and the twist was 0.34. But in fact, this was linear space data, so this analysis is suboptimal, but it's giving you some idea that maybe energy is leaking out of the fundamental. It might be going into the harmonics. And so I'm going to show you results that are log spaced and using multiple harmonics. Okay, so now we're log spaced, and now we've got 4 modes fit. And in this case, I've got the first harmonic, which is twice the fundamental, and then I've got the double of that, which is 4 times the fundamental, and then I've used a subharmonic to see if there was any power there. So it's half of the main frequency, so it's a longer mode in time. And here we see this quite a nice fit. The total twist is this orange line. It fits very well for 2011, 2013, 2017. It even has this little bubble in 2019, which it turns out has some subharmonic energy in it. And then it does less well in 2021, but to the extent that it does fit, it's because of that first harmonic at twice the fundamental, or the first overtone. And in this case, 61% of the energy is in the twist and 39% is in everything else, which is the Writhe. And this just shows conceptually what the 4 modes look like. These are not normalized to their energies. They're just, well, you can actually see their energies, but there's different scale on each of those. So the scale on the fundamental, which is the second one, is going up to 0.4, whereas the subharmonic, it's only going to 0.1. And for the second harmonic, which is 4 times the core frequency, it's going up to 0.1, etc. And you can see how they kind of line up with the bubbles. I've shown the bubbles as these gray vertical lines. And so you can see that the 2011 bubble lines up with the rising portion of the fundamental, the rising portion of the first harmonic, and not so much the second harmonic. The 2013 bubble lines up towards the peak of the subharmonic, a rising portion towards the peak of the fundamental, a rising portion of the first harmonic. The 2017 lines up with the rising portion of the fundamental. It's at the bottom of a subharmonic and starting to turn up. The first harmonic has turned up and is rising, and the second harmonic is at the rising portion, but right near the peak. So pretty good constructive support from those different modes. And then the fourth one is 2021. And here we see the subharmonic is rising, the fundamentals falling, the first harmonic's at the bottom, but turning around and then giving support. And then we're also rising with the second harmonic, which is the 4 times the frequency mode, the way I've defined it. And then the dashed line is the second peak. So that's a double bubble. And so the solid line is the peak in the spring of 2021, and the dashed line is in the fourth quarter of 2021. And so you can see how the first harmonic is supportive for that kind of double bubble model. Okay, this shows the global energy fractions in the different modes. So it's well over half is in the harmonic, which is the 1.0 mode. There's not much energy in, sorry, the fundamental is the 1.0 mode. The 2.0 harmonic has very little energy. The 4.0 harmonic has a modest amount. The subharmonic has a modest amount. And then the ride has a 40%, close to 40%. Now, the next one, which is the bar charts that are colored, shows over 3 different time periods how the distribution of energy evolved. And here I divide it into zones of logarithmic time duration. So each one has a width in the natural log of time or age of 0.81, which is a ratio of age of 2.25. But you can see what dates they correspond to are marked at the bottom. The middle of 2010 until spring of 2012, spring of 2012 until middle of 2016, or actually third quarter of 2016. And then, almost the last 10 years for the last one, because again, we want to look at what happens in logarithmic time space. And what we see is that the subharmonic was fairly important in the first zone. At that time, the subharmonic duration was not that long. But by now, the subharmonic has become very long. It's close to 20 years duration for a full cycle. But in that first zone, that and the fundamental, the orange color, were dominating. And then the next overtone was the next contribution, and the ride was quite small. And then in the middle zone, and in the later zone, the subharmonic becomes significantly less important. The fundamental is very strong, and the ride is increased. And then the harmonics are there, but not contributing too much. But then interestingly, by zone 3, the time scale is getting longer and longer in logarithmic time. And so the harmonic importance has fallen, and a lot of energy, the fundamental importance, the orange color, has fallen, and a lot of energy has gone into the first harmonic, which is the green color, the 2 times the fundamental frequency. And then the ride has stayed about constant, and some energy has gone into the even higher harmonic at 4 times the fundamental. So that's interesting. It's not a thorough investigation. It deserves more study, but it's interesting indication. Now, let's suppose that there is a linear component, and that linear component might be a Fourier driver, and it might be due to halvings, which actually are spaced at about 3.75, 3.8 years on average, but more and more spaced 4 years apart. Or it might be due to macro, the business cycle, the refinancing cycle, which looks like it's about 5 years in global macro. What happens? Well, you've got 2 phases that are interacting and sometimes constructively interfering, boosting one another, and sometimes destructive. And so this just shows how the phase changes between those two. Here, the big omega is the Fourier cycle frequency. So you say omega t equals 2 pi when t is 4 years. That's what that value of omega is. It's just pi over 2 for the capital omega. The small omega is around 9, and that's our log periodic frequency. And of course, that multiplies the log of time. So this is just illustrative. I've used a small omega of 9, and I've used the Fourier driver, 2 pi over 4 or pi over 2. And then how does the phase difference change? And so on the y-axis, we have radians. And on the x-axis, we have logarithmic time, but I've shown you the linear time in years below that. And you can see what happens. And I assume just 0 phase in the beginning for these. And so you start out where they're in phase very early on, but then they're out of phase by age 2 because it's -3, which is minus pi, basically. And then, the difference grows until they're back in phase again. You get down to a -6.28, which is -2 pi, which is the same as 0 cyclically. And you're back to, in phase around age 5. And then you've got a bottom there, and then it reverses, and it heads up to be out of phase again around age 10 or 11, which would be the year 2020 and 2021. We're basically getting into where that 2021 double bubble is. So we were out of phase with any possible linear driver. So the idea is that the writhe components are exogenous driving forces that may have macro influences. There may be a halving cycle. Now, halving is both endogenous and exogenous. It's defined by the Bitcoin protocol, by the Nakamoto consensus. So that part's endogenous. But the way people act around the halving, if they have a herding instinct, and the way they respond to that and trade around that, that's exogenous. And then as time goes on, we rose, higher and higher. And now by around age 13 years or so, we were back in phase, and then you're getting further out of phase as time goes on there. So that's just kind of conceptual, but it's also something that could be explored in more detail. Okay, this is a summary slide. The twist and writhe of Bitcoin, the price trajectory can be viewed as the topological filament. It's the core, and its deformation decomposes into the twist component, the log periodicity, and those modes carry most of the energy during bubbles. And the writhe component is the residual non-coherent exogenous distortions around the backbone. The 2021 double bubble reflected a loss of fundamental twist alignment. We kind of saw that in the phase diagram before. And that forces deformation into higher modes. And we also saw some of that when I showed you the color bars, with the 3 different errors. Now, the persistence of stable scaling parameters suggests the presence of restoring dynamics. Here I've used the analogy with the hooks. When Paul rides the sandworm, it's just a crude analogy, but they constrain the system to the manifold. And that mechanism is not directly observable, but it's reflected in this coupling invariant, this coupling constant that we've discovered for Bitcoin, that basically is a multiplier between the power law exponent, here denoted K, or in our paper we call it beta, times the logarithm of the log periodic spacing parameter. You can also write this equation in terms of K and the angular frequency omega, and there's a 2 pi in here. So that coupling constant is a hidden variable that underlies, but couples both the continuous scale invariance of the power law and the discrete scale invariance of its log periodicity. Power law anchor, log periodic modes twist, writhe residual deformation, and hooks are the mechanism that keep the system close to the structured manifold. And with that, thank you very much.
Great, very interesting presentation. I really love this analysis because I think it goes to the core of how these cycles should be studied, because you have all kind of different positions, right, on X space, is where most of these discussions take place, or maybe on YouTube. And there are usually 2 camps, right? There is the camp that says, oh, the 4-year cycle, it's an illusion, didn't exist, it was never there. Other people say, no, it continues, so then some people talk about an extended cycle, but without really any evidence. And what we are showing is the proper way of studying these cycles, understanding them scientifically, because the data is there. And we, physicists are very acquainted with understanding cycles. That is in our toolbox. One of the things that we need to do eventually is to look at the coupling with different external cycles. We are not doing yet, but there is evidence that this changing in power of different modes, and explaining in simple terms, and Stephen, you can correct me, the mode represents different type of frequency, right? So, for example, we have not just the 4 years, let's say 4 year related cycle or 4 year cycle in terms of scale, the scale of 4 years, but we have oscillations of all kinds, right? A natural oscillation is the day. I'm sure it's easy to track that there is some change in price over a day simply because humans are associated with our daily cycles. Now, Bitcoin is traded all over the world, so maybe the daily cycle are not strong as, for example, with Nasdaq or the other stocks because there is a precise opening of the market and closing of the market that doesn't happen with Bitcoin. But one of the strongest market is in the United States, and most people go to sleep at night. And sure, there is some trading happening in the East, but it's not as big as the one in the United States, so has different type of flavor. So there are these cycles, there are monthly cycles. All these things are there present, and the different modes represent them. What is interesting though is that there is this slowing down that is typical of log periodic oscillations, and the signal is so strong and so present, and it's not easy to reproduce because to have I will show you in a moment some very interesting slide to show that this changing frequency is happening at very precise way and consistent in all these modes is not something that can be replicated by noise. It has to be a signal, a real signal. So it's very, very specific. And this also solves a little bit the problem of having a few oscillations, because when you go to this higher frequency, then we do have a lot of oscillation. We start to have a lot of oscillations because, even if you have a mode that is 2 times stronger than the normal mode, you're starting to see maybe 8 oscillations in the 16 years of history of Bitcoin. So you can start to do some real statistic with it. And so there are a lot of interesting things to say about this approach. Maybe, the fact that the institutions are coming in, are bringing faster oscillations because there is maybe more interactions with the markets, the normal markets. These are things that need to be studied. But it's instead of having some people expressing opinions or feelings or using a bunch of words, we are using data, and this is the correct way of doing it. And by the way, Stephen, I found myself as one of the things that I found in my studies that yes, there is a redistribution of energy or amplitude in the modes. The faster frequencies seem to be stronger recently. So I verify the same result, but with slightly different approach. In fact, I can show some slides where I can discuss some of these ideas. By the way, I'm going to be at the Las Vegas conference. This conference starts next week on Monday, and I will be there. There will be a booth. I will be both with the Minotaur. They have a booth over there, the Minotaur trading company, but also with Blockstream. I'm working with as an advisor for their fund. They have actually a power law based fund. This is an organization associated with Blockstream. It's called Blockstream Capital Patterns, and they develop a power law based fund. And so I am an advisor with them, and I will be there with them in the Blockstream booth, and I'm going to have a bunch of books. And so if people want to have a physical copy of a book, I will sign it for you, and we can discuss it. And I will be present there. Anyway, so I want to show you a couple of things. First of all, I did these are simulations that I showed you last week. I move the slides around just a second. Okay, so this one is interesting. Let me show you this one. We saw the previous one the last time. But this is, I'm showing actually the log periodic oscillations in this complex space. It's it's more a curiosity than, at least right now, maybe there is not much useful to it. If you show just in the fundamental mode, what is interesting is that in the plane, so just let me explain this graph, right? So we explained many times that we can write the two fundamental power law, the power law that is the long-term power law, and then these oscillations can be also written as a power law with a complex exponent. And then basically these oscillations are happening in this space where you have an imaginary component and a real component. And you can see the projections of these oscillations in this complex space in these three planes. One is the plane where we live, that is a real plane, right? Real time and real price, right? So this is the floor of this box that you're going to see basically the log periodic oscillations and the price of Bitcoin that exist in that place. But it's really cool because in this way you can see there is something else happening. It's an abstraction, but there is these oscillations that can be understood some kind of almost like an helix that is happening in this complex space that has both an oscillatory component and a long-term component. And these, here in that on this panel here on this wall of this box, you're going to see the imaginary versus time. The floor is real versus time, and then this back wall on the left is imaginary versus real. What is interesting when I do the same thing that you're doing here, I'm showing all the different modes. It's a little cheating version relatively to what Steve does, because I'm actually using the observe frequency, not just modes of a main one. And it's cheating because you're doing this after the fact, right? While with the normal mode, because it's dominant, you can make the assumption that there are higher frequency, and these, there is not really a look ahead in that approach. But here I'm not trying to make a prediction, I'm trying to characterize. So it's okay to use this frequency to characterize the oscillations, and the fact they are not precise, the multiples of the main mode is telling us something. So probably some kind of interference with one possible explanation, it's interference with some external oscillations, like the one we see in the microeconomics, for example. Something that needs to be understood and studied. It's an interesting graph, and I was telling you that if you focus on the real versus imaginary panel, and you plot only the main mode, these oscillations look periodic when you plot them in terms of the log of price. So both the log of price and the log of time show this periodic oscillation. That is really cool. I don't know if I understand completely why the log of price, because basically they are proportional to each other. That is really, if they are periodic in the log of price, that is the scaling in the price, then they should be also, if they are periodic in the scale of time, they should also be periodic in the scale of price, right? They are proportional to each other. And this is shown by this panel here, the imaginary versus real. It is really cool. But anyway, I will show you how the visualization looks like. Let me run it. So there are these kind of like an helix oscillating around the power law. You can see the projection. So what we are observing in the real world is a projection of this more complex type of behavior. So it's interesting. And the complications, so basically it's the same structure, right? You're seeing this structure here, it is basically three peaks that is repeated over time. This is why we call it log periodic. But notice how it's been stretched, right? So these three peaks are very close to each other here. When the same type of structure, these three peaks, is repeated here, but now it looks like almost like a rubber band. We are stretching this structure, and then we are doing it even more. Now, one interesting thing that also Steve is commenting, what we considered two peaks, the one in 2018 and the one in 2022, were actually part of the same structure. And the reason why we have two peaks is because we have these subharmonics. They are basically sub oscillations of one big oscillation. It was this big event here, right? And notice how actually it's really interesting because part of the structure is this middle peak. It was between the two peaks of 2018 and 2022. There was this bump here that actually is explained perfectly by this log periodic model as one of the three oscillations. So you have the addition of these modes creates a more. It's not just one single peak. It's three mini bubbles, if you want. And there is one in the middle that is not possible to explain if you don't have something like this. That is really cool.
Yeah.
Anyway, this is how these oscillations look like. They look complicated. When you do only the one mode, they look much simpler. For example, in this space, they look simply like three peaks that are periodic in this log of price space. But yeah, there is much more complexity when you add this mode. But notice it's basically the same structure. It's just that this interference between the main different modes. In this case, I'm adding 5 harmonics, create this complexity. But it's simply the addition and subtractions. When we are in phase, when we see a big, huge bubble, is because these modes are in phase. And when we don't see them, is because they cancel each other. Okay, so this graph is very interesting. So what I'm doing here, it's kind of what I was explaining before, but in a different way. So I'm looking at what is called a spectrogram. So basically, I'm plotting how the different contributions of a log periodic frequency happen in time. So we are having time in the x-axis, actually the log of time. Here are the dates, and this is the quantity itself, right? And so we are in this space where I'm taking the log of the frequency and the log of time. Now, the contributions of this log periodic frequency, they should look like straight line. It's basically very similar. So this is one of these affinity space where things became simple, right? We have mentioned it in the past. You go to some spaces where the complication of Bitcoin behavior became simple. One of the spaces is the log of price versus the log of time. And what seemed very complicated looks like a straight line, like a nice, simple straight line. And you can do this with these oscillations of the bubbles. And you go to this space where everything seems simple. In fact, they are just line, straight line, flat line. And the dominant flat line is these dominant cycles that Stephen is talking about all the time. It looks like a straight line. And you can see, so this is where the theory says it should be, this line. And this red color indicates, so it doesn't know, you see this calculation that we do in the background, right? It is producing this color map, is simply associating, in this case, decibel, right? How strong the energy associated with this oscillation. So it doesn't know anything about this log periodicity. We are not introducing it by force. It just comes out by the analysis. We are doing this kind of Fourier analysis in this. This actually is more like a wavelet analysis, but similar idea. we are basically trying to calculate the contribution of different frequency in terms of how the price looks like, the and color code strong oscillations in red and weak ones, right? Lack of energy with lighter colors like blue and white and so on. And you can see there is a very clear signal here at this line where the main mode is. And it's so cool because it looks like a straight line. It's impossible to create these by some artifact or noise. It's a super clear signal.
And that energy level is in this set of units, it's 3.2. So
Yeah.
the frequency in cycles per log decade is 3.2. That corresponds exactly to angular frequency 8.75
Right.
that we find from the log periodic.
And you can see it was very strong in this region. I put stars where the bubble is. So it was very, very, very strong at this particular bubble, that is the 2013 bubble.
I'm back. So that 3.2 that you see in...
Yeah, we lost you, Stephen.
Can you hear me?
Yeah, now, yes. 3.2 here in the time. I don't know if you are saying something, but we cannot hear you. Try to say something. Stephen? Hello? I don't know if Stephen hears me. Probably not.
Okay, how about now?
Yeah, and now we hear you well. Okay, go ahead. Say what you have to say.
Well, I was saying that primary level, that band, is at 3.2 cycles per decade. And that corresponds precisely, 3.21 corresponds to 8.75 in angular frequency terms.
Yeah,
which corresponds to 2.05 log periodic spacing. So it's right on top.
Yeah. And you can see it became like what Stephen was saying, becoming weaker here, right? Because you can see it's a lighter, it's still strong, it's still an orange reddish color, but it's not as strong as here. So it's becoming weaker, right, with time. And it's being picked up by this higher frequency. Like you can see also here, there is this empty space here. So there is no match between this frequency and the next. And then this is a second harmonic. And you can see it's not as strong as this one, but it's very clearly visible there. So, and this is the third harmonic, and the fourth. So you can see it's a real signal, in particular the main frequency. There is no doubt there is a log periodic. I mean, we have played with this kind of things so much in our career that I can tell you, I studied so many other phenomena in my life that are cyclic. You don't see such clear demonstration of this. Like, for example, I did studies with brain waves, right, where you're expecting certain type of brain waves, like, for example, these slow waves being in a certain range. People publish paper, and the signal there, they do spectrograms like that. There is never something as clear as this. This is a clear, strong signal, and also it's not based on just measuring the oscillations in a certain range of time, right? Because you say, oh, there are only 3 oscillations. Here, this is a continuous signal. It's a continuous signal. It's present all the time. Now, there are some limitations. Yes, you're still relying on how many cycles you have, but it's you compare it. You compare it what you are expecting moment by moment. So you have a lot of data points. It's a continuous signal. Doing it in this way, a spectrogram. This is why people do it. It's not just, oh, I count 3 cycles. Well, okay, it's not enough to do statistic. No, you're measuring it in a continuous fashion, and you can show that there is nothing else in between. But I think it is a very powerful graph, publishable. Eventually, we will publish a paper on this log periodic idea, And this will be one of the things that we will use to demonstrate that this signal is not something that we are making up. It's overfitting, etc. It's a clear signal. Yeah. In particular, I like this transformation. Is again one of these affinity spaces where the data becomes simple, right? You do this log periodic spectrogram, but I never saw one actually, to be honest. Uh, but it's with Bitcoin works very well, So this is similar to when you see the power
Yeah.
law as a straight line in the
Yeah.
log graph. It's a very similar idea. It's the equivalent of that because it became so simple, right?
If you did this in brainwave research, it would be prize winning if you saw a
Right.
signal like that.
Yes, exactly.
Yeah.
Yeah, and it's so even just the present. Now, one can discuss the subharmonic. Are there, not there? I think they are, but the main um, oscillations is so evident and clear. This is publishable work, and it's interesting because this will be so fascinating that there are all these power laws, so this scaling behavior that are driving Bitcoin. It's not just the main power law, it's also this more subtle power law that is associated with the cycles. And yes, I'm pretty sure that the cycles interact in endogenous. I like this word that Stephen uses all the time. Endogenous cycles interact with the external world, but this log periodic one, it's endogenous. It doesn't have anything to do with external oscillations. It comes from this why is a power law itself. It comes from the internal mechanism of how Bitcoin behaves. And this log periodic is not periodic. So when people evoke the 4-year cycle, now what happened is probably because it's close to that 4 years, right? It contains the 4 years in one of these subharmonic. So as the main cycle becomes longer and longer, it can contain these sub frequencies like 4 years, for example. So this is why it's not really an illusion that it was for some time. It was some kind of locking with the 4-year cycle for some time, the last ones that we observed. But now we are leaving that behind, right? Because these main cycles is becoming longer. So it's going to 8 years, 16 years, and so on. But inside, you can still see this subharmonic operating, maybe becoming stronger. And this is why you still see oscillations that are on the order of 4 years. So it's not really, the answer is neither. The 4 years, it's real, but the in normal interpretation that people give is not correct. It's not a main frequency inherent in how Bitcoins behave. It's a more complicated picture. It's a more nuanced picture. Is this your understanding too, Stephen?
Yes. Can I show a table?
Yeah, absolutely.
It kind of speaks to it a little bit. Let's see, window. I think it's this one. Are you? I'm not seeing it. Are you seeing the table?
No. Let's see. Yeah, I see it
again.
Yeah. No, I see it. Okay.
Okay, that one. Yeah. Okay. So this is, I showed you. So imagine you have age 2, 4, 8, and 16. And then in the next column, you've got omega of 9 times log of age. You get these numbers: 6.2, 12.5, 18.7, 24.95. In other words, they're spaced uniformly because I'm doubling the age, right?
Mm-hmm.
And then you ask, what is the 4-year cycle? So here, omega, I've chosen to be a 4-year cycle. So when t is 2 years, it's pi, it's 3.14. And when it's 4 years, it's 2 pi. So you've gone through one cycle, it's 6.28.
Right.
At 8, it's 12.5. At 16, it's 25. Well, look how those compare. And what's the ratio of the second column and the third column? That's given in the last column. It's this M. It's the number of modes that you've moved through.
Right.
And so there's a coincidence. At age 2, it's 0.5. At age 4, it's also 0.5. And that's because 4 is the square of 2. That's why that happens.
Right.
And 8 is not the square of 4. So the next one's 0.67, and the next one's 1.1. So you can see it moves from being half a cycle to a full cycle, as I showed on the graph before.
Yes.
So this number of modes is measuring how it interacts. And you can extend this to think about the harmonics. Is M equal to 2? It's going to interact with that first harmonic, right?
Exactly. Constructively or destructively. Yes.
Yeah, constructively, collectively contribute to each other.
Right.
So this is showing the principle of that. And it's also sort of showing how you could kind of have been locked in around 4 years for
a
couple
so it's
of
not an illusion, it's real, but it's not really a fundamental thing. Of course, there is also the halving cycle, etc., that probably has a contribution. It needs to be studied, but there's some kind of cycle in Bitcoin that it looks like superficially like the 4-year cycle, but it's not. It has this subharmonic, they interfere with each other, and this explains things like having peaks in the middle for when we had a peak, a small peak between 2018 and 2022. It explains why sometimes the peak doesn't happen at the same place at the same time. It's more complicated. The next thing that need to be studied is really to see how these modes interact with external cycles, because I see all the time, for example, people superimposing. It's not a new thing, but now it's a new grail, right? Of looking at the PMI, for example, we say, hey, they look almost identical. Well, because Bitcoin had only a couple of oscillations, and maybe they locked, for a short time, because when you have two similar frequencies, they can lock each other. They can follow the same phase, and it makes sense that Bitcoin follows some macroeconomics. But I'm already seeing some decoupling, because the PMI cycle is going up pretty fast right now, and Bitcoin is not really following.
Mm-hmm.
So it's something that needs to be understood better, But it's not a question of the external cycle are driving Bitcoin. There is some interaction, but it's not one-to-one, Where Bitcoin has its own, what we are trying to say, that Bitcoin has its own internal cycle. And if somebody says, well, it's all due to liquidity, it's all due to PMI, they are not telling you the true story.
I disagree with that, because I've measured liquidity. I used the OECD M3. I've measured the PMI. I measured the Chicago Fed Financial Conditions Index. And of the three, the best is the last one, the Financial Conditions Index. And it's a very rapid one. Right. It's available weekly. And Bitcoin responds rapidly to changes in financial conditions. The liquidity one is very slow and backwards looking, because that's affected by central bank policy. And they're looking at the past, like a couple of quarters before they even make a decision,
right,
and change their liquidity. And the PMI is only available monthly, and is also kind of lagging. And neither of those first two have significant power relative to either the fundamental or the first harmonic.
Yeah.
And the ANFCI, there is some signal, but it's also relatively small. It's down below the first harmonic.
Yeah, we will need to go deeper and look at, there are different tools that we can use, some coupling, thinking about it like if there were some oscillators and they are coupled by a spring in between, and we can study things like that. And, this probably that is the next step in our exploration. Anyway, guys, I don't see any very relevant question. It's okay. So maybe we can skip the answering question part. And yeah, I think these are very interesting studies. I know that they seem very details, and we use a terminology that maybe people don't understand, but it's the right way to do it, because it's a very interesting topic, and the more superficial explanation don't cut it. So anyway, guys, remember to please to subscribe and to like this video, and we will see you next week. And if you are in Las Vegas, please come to see me. I would like to meet you. Thank you so much.